9.3, estimating population standard deviation. We're going to go into chi-square distributions, which took me a while to understand, so I'm going to be teaching you what it is and how it was pretty much derived. So first, important to know that we're dealing with variation or standard deviation squared distributions. So variance is just the same thing as standard deviation squared. Let's first compute the variation for or variance for each of the 2,000 samples. So let's say we have a normal distribution, and we only use chi-square distributions for normal distributions, which makes it a lot easier to understand. And it's quite genius, actually. So, and we'll truncate the x-axis, so it starts at 0, and this will be 1 standard deviation, this will be negative 1 standard deviation, and this will be negative 2 standard deviation, and 2 standard deviation. Empirical rule, pretty easy. I mean, we didn't really go into the area of the curve, but that's what a normal distribution looks like. So let's say we take 2,000 samples, and we get this distribution, which you will, and let's say it's normally distributed with a sample size of 10, standard deviation of 15, so this is actually at 15, and this is what we're doing with. So first, what is a chi-square? Now the chi-square formula, sorry, I don't think this is the right notation. I'm not really too sure about the notation. It's, sorry, it's not z, it's x, a curved x. So what is it? Well, simply put, it's going to be for discrete values, by the way. So it's simply going to be a z-score squared. Now, what does that look like on a formula? And that formula is going to look like degrees of freedom, which is n minus 1, times the sample deviation, which we'll write like that, and a population deviation, which we'll write p that. So it's quite genius. So first, why did we square it? Now, we square it because of two things. And also summation notation of all the z-score squared. So why do we square it? So first, imagine that you have a set, 5 data sets, and we'll list them as x1, x2, x3, x4, and x5. And let's say that we get a standard deviation of 2 here, standard deviation of negative 1, a standard deviation of 3, which these are actually pretty huge standard deviations if we're talking about z-scores. And we are. Let's get negative 2, and then let's get like negative 1. Now if we add them all together, what happens here? And this is what a chi distribution is, because I guess we're not squaring it yet. We get 1. So is it safe to say that the chi-scores or all the standard deviations summed up is 1? And no, it's not, because the negative values cancel out the positive values since we have a truncated x-axis. So instead, we square them. And that makes the values a lot more meaningful. So we have 4, 5, 9, 3 squared is 9, which is 14. Sorry, let me do the math. So it's going to be 4, 5, 14, 15, and 19. So now we have 19 standard deviations, which is pretty nice to understand. So that's what a chi-square distribution is. Chi-square distribution is simply going to be a distribution of all the standard deviations squared. So why does it work? So first, let's look at the x-axis. And the x-axis in a normal distribution is just going to be standard deviations. And this tells you how far it is away from the relative data set. So let's go back to the chi-squared formula. And the chi-squared formula is just going to be the degrees of freedom, which is n minus 1, times times sample variance, and I don't know, okay, squared, and then population variance squared. So an issue arises because we can't calculate the population variance. So how can we just see the shape of the graph for a chi-squared distribution if we can't calculate each chi-squared formula? And simply put, we just use the original distribution. And since we're squaring all the values, there's no such thing as a negative squared standard deviation or negative squared z-score. It's just right infinity here. So it's all greater than 0 because anytime you square a negative value, it becomes positive. So it's important to note that the only determiner of the chi-square line, curved line, is going to be the degrees of freedom. And why is that the case? It's a little bit abstract to understand, so we'll use some logic here to kind of get into this. So first, you can't calculate it like this, although this is the typical formula. So if we take one standard deviation and we square it, we still get 1. And if we square -1, we still get -1. And let's actually go over some notation here. And let me delete this normal distribution graph so we can focus on the chi-square distribution. Let's go over some normal notation here. So the x-axis is just going to be the chi-squared. So what each chi-squared value is. And the y-axis is going to be density. Or how much when you times it by the x-axis, how many the probability, pretty much, as we know, that's what the area under a curve is. So why can we just use this? And why don't we need the why is the degrees of freedom the only determiner of the curve? So I believe a degree of freedom of n equals 2 looks something like this. And like this, and then df minus 2 is where the peak, where the degrees of freedom minus 2 or n minus 3 is going to be where the curve peaks. So why is it this case? Well, note that the chi-square distribution uses a z-score, which measures how far it is from the standard deviation. So when using normal distributions, every point is going to be a certain distance away depending on the z-score. And the z-score is going to be basically a standardization method. So it doesn't matter about these values here. Because the distribution is always going to have a normal distribution which follows the empirical rule. 68% of data within the first standard deviation, 95 in 2, and 99.5 beyond that, or within 3. So theoretically speaking, we have a lot of chi distributions right here, or 2, or 3, or it's 1, 2, 3, 4, 5, etc. And the highest one is going to be a certain. They're all going to be the same shape. And this is because the chi-square deviation still deals with standard deviation here. And since each normal distribution is scaled relative to standard deviations, which basically allow you to calculate the probability under anything, because we're using the standard deviation, which standardizes the distributions and the z-scores. So that's pretty much the logic behind it. It's a little bit abstract, obviously, but that's how I figured out what it means. Here's the formula that I already explained. So this is the formula here. It's simply just a squared a chi-square distribution is just the distribution of squared standard deviations, or squared z-scores, should I say. Here's an example. So chi-square is here, and the shape looks something like that, because the degrees of freedom should be somewhere around 10 here, using some logic, because df minus 2 is where it peaks. So it's not symmetric because most of the squared values are going to be positive, meaning it's going to be somewhere around here. It's always going to be skewed, right? So that's some logic. As the number of degrees of freedom increases, the chi-square distribution becomes more nearly symmetric, since that overpowers the variation. Let's go back to the original chi-squared formula. And we get chi-squared, sorry, it's a squiggly x. We get chi-squared is equal to degrees of freedom times the population, or sample standard deviation times the population standard deviation. As this gets infinitely bigger, or variance, I guess, sorry, not standard deviation, it's going to overpower the rest of this, which makes the x squared go to a certain point. So yeah, that means the score contributes less using some simple mathematics. here's what the graph looks like. As you can see, let's use some logic here. With 10 degrees of freedom, which is going to be this orange curve, 10 minus 2, that's typically where the peak is. I'm not sure why that works actually, so I'm not going to be explaining that at all because, I don't know, you can look at someone else's explanation of that. Since the chi distribution is not symmetric and basically only has positive values, we cannot construct a confidence interval using the point estimate plus or minus the margin of error. Instead, use a table with the right degrees of freedom to calculate the critical values and their corresponding probabilities. So let's say that we calculate a sample variance using a sample, which is just standard deviation squared, again. And then we find it on this graph right here. And then we just use a chi-squared distribution to see what chi-squared corresponds to which deviation. And since chi-squared are simply the squares of the z-scores, they're all going to be relative to the standard deviation. So you don't have to worry about the graph looking different each time, as mentioned before. And then you calculate the area under the curve. And the difference here is that we don't start by 0 and we don't use the plus or minus notation. Instead, we just use kind of like in applied mathematics when you denote the domain and range, something like that, with the max value and the min value, and with the confidence interval. And the formula is the same way. So if we get the confidence interval of, let's say right here, 0.5 and 0.95. So I'm actually kind of confused why. Oh, okay, there we go. So 0.95 because it calculates the area to the right, I think. Wait, let me use some logic here. Okay, so you just take this variance here, and it'll give you the max variance, or the max chi-squared distribution, which is just variance. So min variance, comma max variance, with this with the confidence interval when you look it up in a chart, and the min variance is gonna be this here, which is just squared. So to get the standard deviation, we could just square root both sides, and that's pretty much it. So since the x-axis is gonna give us the chi-square, which is just z-score squared. It's always gonna be positive. That's first, and it's always gonna give us the population standard deviation. So when we get a confidence interval, we're basically denoting between what values the actual population variance is in, giving that confidence interval in terms of chi-squares. And then since chi-squares are just sample variances, you just square root them to get the sample standard deviation. It's pretty genius, and like I'm pretty surprised that people figured this out. So